So looking at one of our conservation laws, so we have two basic conservation laws of mechanics, principal conservation of energy and the principal conservation of momentum. So principal conservation of energy, mathematically we use this when there is a change in height of something. Either something is falling or it's changing height, it's going up or it's going down, and we can use our conservation laws. So remember, there are two mechanical energies that we're interested in. Number one is kinetic energy, okay, so energy due to motion, and the formula for that, E is equal to half mv squared. Okay, m the mass, v the velocity. Clearly, if your velocity is zero, you have no kinetic energy because the right hand side becomes zero, so that's your formula. So mass E is equal to half mv squared in the tables. And gravitational potential energy is the second one we'll be using for calculations, which is potential energy due to position. Now remember, there are other types of potential energy, like elastic potential energy, which you'd have if you compress a spring, but in this case, in the calculations, we will be dealing primarily with gravitational potential energy. Okay, and that is mgh, where m is the mass, g is the acceleration due to gravity, which will always be given to you, 9.81 meters per second squared, and h is the height difference to create the potential energy. Right, so that's it. So we've looked at that before. We have that idea. Then, in a situation where there's a change in height, we can have the general formula. Okay, in other words, that we can say the potential energy. Okay, I'll call that EK and EP. EK plus EP, the kinetic and potential energy before, is equal to the kinetic and the potential energy after. Okay, right. Now, kinetic energy before, remember, if we're talking about initial and final velocities, we generally call the initial velocity U and the final velocity V. So the initial kinetic energy will be a half mu squared. Initial kinetic energy, okay, will be mg h1. Okay, we'll call it h1, the first height. And the kinetic energy afterwards we'll have kinetic energy, potential energy, so it'll be a half mv squared plus mg h2. And that's the general formula. Okay, so it's not given to you directly in the maths tables, but you can get it from here. Okay, if you're in TY, I'll be giving that to you. Right. Okay, so that's your formula. That's where we're going. Okay, so I'm just going to move that formula to the top of the page, and then we're going to do a few calculations on it. Okay, so we're back. So look at the question. An object falls from a height of 50 meters to the ground. What is its maximum speed as it falls? Okay, and I should give you the acceleration due to gravity, so I'm just going to write here as g is 9.8 meters per second squared. Okay, that's all it's going to be there, but it will always be given to you. You know it, so I won't be giving it to you anymore. Okay, right. So as always, on the left hand side we write down what we're given. Okay, now this looks a bit interesting in that there's no sign of a mass. Okay, so remember, mass very often can just be cancelled in this. Okay, so we won't worry until we have to worry. Okay, we have the initial velocity. It falls from, no, it just says it falls. You can assume it falls from rest unless they tell you otherwise. So the initial velocity is 0. The height is 50 meters to the ground. Okay, so we will call height 1 50, and we decide what the 0 position is, and usually we'll use the ground as a 0 position, so in this case h2 is 0. Lots of zeros, doesn't matter. We're using the general formula here, which always works. Okay, some of you will do simplified versions as we go. That's fine, but the general formula always works. Okay, and we're asked for the maximum speed. Now, think about it. If we drop an object, okay, if I drop an object, okay, it'll increase speed as it falls, and it's at the maximum speed just as it hits the ground, just before it hits the ground. Okay, so we want the final velocity effectively. Okay, right? The end. Okay, so that's all we've been given. So we write down, okay, the total energy before, the initial velocity plus the initial potential energy. Total energy after, still the same. The final velocity, because it's the initial energy, the initial potential energy, initial kinetic energy, initial potential energy, our final kinetic energy, half mv squared, final potential energy, mgh2. Okay, now, rather than filling in zeros, what I like to do is I just do cancelling when we can cancel. Okay, so let's have a look. The initial velocity is 0, so pretty clearly I can fill in 0 here and this disappears. So if you have a 0, when you multiply them together, you're going to get 0. Okay, so we just cancel it, just draw a line and cancel it. The initial potential energy does exist, so that's mg. I'll just write it down like this. Kinetic energy, it does have kinetic energy just as it hits, just before it hits the ground, so half mv squared, and h2 is 0, so the mg, that section mgh2 will multiply out to be 0. Okay, so that's gone. So suddenly the formula becomes much easier. Now, on top of that then, the mass before and the mass after. So the object is falling, it has a certain mass at the beginning, it has a certain mass at the end, the mass is the same, so this mass and this mass are the same, so we can cancel them. We can divide both sides by m, or just cancel, and we're left with gh1 equals a half v squared. And suddenly we've gone from there to there. Okay, so you have two ways of doing that. You do it my way, this way, or you could put in your zeros and they'd all disappear out. I think this is the better way to do it. Okay, but always start, I'm suggesting you always start with that. Okay, so we've gh1 equals a half v squared. Okay, and now we can start filling in. So we've 9.8, the original height was 50, equals a half, and the final velocity. And suddenly, okay, so we have, that's 490, isn't it? Okay, equals a half v squared. So multiply across by 2, so we get 980 is equal to v squared. We get v is the square root of 980. And we get the square root of 980. So square root of 980, and we're getting an answer of 31.3 meters per second. And because we put in the correct units at the beginning, we're getting the correct units out at the end. So that's the first example. And remember, why are we using this method? We're using this method because there is a change in height. Okay, we're going to do one more now. Okay, and we'll which will be a little bit more involved in it, and we'll see where we go after that. Okay, so here's the second one. A pendulum passes its lowest point at a speed of 4 meters per second. So the pendulum is moving this way. Okay, it's swinging. Okay, what is the maximum height above the ground that it will reach? Above the ground. Okay, so there are several ways of looking at this, but we're going to stick with this method. Now this sounds complicated because the pendulum is moving in a circle, so do we have to use circular motion? The pendulum can act as a simple harmonic oscillator, so do we use simple harmonic motion? Or, and this is the big one we have to remember regarding these questions, if there's a change in height, will the principle of conservation of energy save us? And in this case, the principle of conservation of energy will indeed save us. Okay, so we're talking about, okay, what was the total potential in kinetic energy when it was here? Okay, that's going to be before, at its lowest point, and we're going to find out its potential in kinetic energy at its maximum height, and they will be equal. That's where we go. Okay, so let's have a look. Right? Okay, before. Okay, I'm going to do before and after. Before, okay, its height, and we're going to take the ground. Okay, you can pick whatever you want to be the zero height. We're going to take the ground as the zero height. Okay, the ground will be the zero height. So the height at the beginning, okay, beforehand, is going to be 0.3 of a meter. Notice I've changed from centimeters to meters. Don't forget those things, okay? People are forgetting those, okay? Centimeters to meters, okay? Then we are told it has an initial velocity of 4 meters per second. U is 4, so that's before. Afterwards, okay, what are we doing? Okay, afterwards we know that the height, well, we're looking for the height afterwards, and it's the height above the ground, and since we call the ground 0, we're in business, that will be your answer. We're also looking, okay, so what else do we have afterwards? Well, we have that it's at a maximum height. Now what happens at a maximum height? Remember, if you throw something up at the maximum height when it was there, okay, instantaneously at its maximum height, its velocity was 0. Okay, its velocity was 0. Okay, so we have a velocity of 0. Okay, afterwards, right? So, and we've decided we're going to be saved by the principle of conservation of energy. It's a principle of conservation of energy question. So here we go. Okay, we write down our full formula. kinetic and potential energy before equals kinetic and potential energy after. H1 before, H2 after. Initial velocity U, final velocity V. The masses almost always cancelling. Okay, so let's go through it. Okay, we have, okay, let's do our cancelling. Okay, at the beginning, okay, right, we have, it has a kinetic energy. You know, it doesn't matter what direction, energy does not have a direction. So it has a kinetic energy half, and U is 4 squared. Okay, so I'll tidy that up, that becomes 8m plus mgh, so m times 9.8 and the height is 0.3. Okay, so 9.8 multiplied by 0.3. Okay, and we're getting 2.94. Okay, equals afterwards the kinetic energy, and this is one we can cancel because the kinetic energy afterwards is 0, because as it, our after is the maximum height and the velocity is 0, so that's gone. But we have our mass afterwards by g, which is 9.8 again, and we don't know what the h is. Okay, we could have done it earlier, but we'll do it now. We can cancel all the m's. Okay, and we get 10. We'll almost always be able to cancel the m's. If you're a TY student, the m's will always cancel. Okay, so 10.94 equals 9.8h. Okay, so we're in business, divided across by 9.8, so we get 10.94 divided by 9.8. And we are left with 1.12, and we put everything in meters, so everything comes out in meters. Okay, if you would put in 30 centimeters, it would have been a mess because you'd have used height as 30 centimeters, but your speed was still in meters per second. Gone. Big trouble. So always the correct unit. Don't forget the correct unit. Okay, so just to recap, remember, we use the principle of conservation of energy if there is a change in height. It saves an awful lot of hassle a lot of the time. In this case, if you're not using principle of conservation of energy, the object isn't moving in a straight line, it's moving in a circular motion. It gets very messy. It can be done, it gets very messy. If the principle of conservation of energy is there to dig you out of a hole, use it at every chance you can. Okay, very good. Bye-bye.